There's a tongue twister. Differentiability. Differentiability is a follow-on from continuity, much the same sort of thing. We treat in the same way, but the only difference is, instead of looking at the function as we do in continuity, we're going to look at the derivative of the function. Let's start with the absolute value. The absolute value function, let me remind you of the definition. There's the definition. The absolute value is a bit of a bully. It throws out any negatives. Doesn't like negatives. So if x is positive, then it leaves it fine, and the absolute value just counts as a bracket, nothing else. So if x is greater than or equal to 0, then absolute value of x is x. But if x is less than 0, if x is negative, then it changes its sign and makes it back to a positive. So notice this looks negative, but it's actually a positive number because the actual x represents a negative number. Now we're going to differentiate, but I'm only going to look at the derivative at x equals 0, because that's the point in question. Everywhere else it's fine, but just here. So let's go back to first principles. Substitute x plus h for x. There we are. Now at this stage we can substitute the 0 for x, because we're only looking at the point where x equals 0. Now 0 plus h is h, therefore the absolute value of 0 plus h is absolute value h. Absolute value of 0, goodbye, and we end up with absolute value of h over h. Now we go back to the definition. Absolute value of h, we have two possible cases: h greater than or equal to 0, h less than 0. So we've got to put them there. Right, now when h is greater than or equal to 0, there it is there, then we'll have a positive number, absolute value, and therefore h just stays h. Over h gives you 1. But when h is negative, when h is less than 0, we'll end up with negative h over h, negative 1. Now those are not equal to one another, which means therefore there is no derivative at x equals 0. Because what do we take? Do we take the left or the right? We don't know. So therefore that's the case. Therefore f of x is not differentiable at x equals 0. So a function is differentiable if it can be differentiated at every point in its domain. Let's just be a bit more particular and say it is differentiable if it can be differentiated at every point within the extremes of its domain. There are three different ways to look at it informally from the graph. First of all, as the absolute value if you have corners or kinks. There we are, like that. I wouldn't like to sit there. I would hate to bump my head on that. So if we see that's the case, let's illustrate this. Let's go to a curve. You notice that if we take progressive zooms of this red section, you'll see that it approaches a flat line. It's approaching a flat line. We can take enough of it to make it as close to a flat line as we like. And therefore the limit is a flat line. The left limit of the derivative is 0. The right limit of the derivative is 0. There we are. So the limit is a straight line at the turn. But if we now take a corner or kink or anything sharp, no matter how much we zoom, we're still going to get a pretty lousy injury if we bump our heads. Probably need stitches. So therefore, like as in the absolute value graph, not differentiable when that occurs. So there's our first condition. Second, if the curve has a vertical tangent. Consider the derivative is the rate of change, or the gradient, in other words, gradient of a graph, in other words, the gradient of this tangent. Now for this tangent, the change in y can be anything. We can choose any 2 points, but between any 2 points on that line, the change in x is 0. Change in y over change in x means dividing by 0. Cannot be done. Boom. Therefore, There is no derivative of a vertical line when a graph is a vertical line. Even if it's a single point of inflection as this is, not allowed. Finally, if there's a discontinuity. Oops. There's a jump discontinuity. It jumped down to there and continued. Now if you look at the left limit as x approaches this value, we end up with the y value being that. In other words, there's the left limit. If we take the left limit as x approaches this value, the right limit as x approaches this value, we approach that y value. So the left limit is not equal to the right limit, therefore there is no limit, therefore it is not continuous. If a function is differentiable at a, then it is continuous at a. That's quite useful. So if we're told it's differentiable, then we know it's continuous. But please be warned that it does not mean the converse is true. Have a look at the absolute value graph. It's continuous there. Left limit equals right limit equals 0. Its function value is 0, so the limit is equal to the function value. Therefore it's continuous, but it's not differentiable. We've already found that out. That's informal. Tatty jeans, tatty case. Let's look at the formal case. So here is our original definition of continuity. Now I'm going to overlay that with the definition of differentiability. What's going to happen is we're going to end up with f prime, f prime, f prime, f prime, f prime, f prime. There we are, like that instead. Because now we're looking at the behavior of f prime of x. The limit of f prime as x approaches a and the value of f prime of a. Let's look at an example. This is looking for differentiability at x equals 3. Well, I can see straight away it's not, because that actually is a corner. That straight line going that way means it's a corner, and that's it. So let's tell the professor that, oh, there's a kink in the graph. He'll laugh at you. He'll say, no, forget it, that is not mathematical. This is pure maths here. Prove it. So let's prove it. There's the definition of differentiability. So the first thing is we're going to take the function, the f prime of a, to see whether it's defined or not. So at x equals 3, there's where x equals 3. So therefore we're going to take that as our function at x equals 3. We're going to differentiate it, we're going to substitute 3, and we get 4. Therefore the derivative f prime of 3 equals 4. So that's fine. Let's take the left limit of that derivative. As x tends to 3 from the left side, we're on this graph, therefore we're going to differentiate that, substitute, and we get 4. So the left limit is 4. On the right hand side, we're on this graph, which is a constant of 3. Derivative of a constant is 0, and the limit of 0, no matter what you're approaching, is 0. So notice we have two different limits, 4 and 0, which means in fact that the left limit is not equal to the right limit of the derivative, which means the limit of f prime of x as x tends to 3 does not exist, which means that f of x is not differentiable at x equals 3.